Hello, and welcome to this video on uncertainty and significant figures. Today we're going to take a look at how we take measurements and how many numbers we should actually record and report our numbers to when we do calculations in chemistry. So grab your Cornell notes and let's get started. So the first thing we want to talk about is accuracy and precision. And so accuracy is how close our data is to the actual value. And so if we kind of think about this from a target perspective, we know that we want to be close to the actual value. And so if we think the center is going to be the best value, the closest to the actual value, then if we have a mark right here, that would be very accurate. Okay, but if we had other marks that landed out here, these ones wouldn't be accurate. They're going to be farther away. And so we know that that center one is actually going to be the one that is accurate. Now, on the other side of that, we can have things that are precise, and that's when our data points are close to one another. And so here's another bullseye, and so we can have a whole bunch of data points that are really close to one another right here. And so these guys all collectively together are very precise. They're close together. And so this shows our precision. Okay. Now, we can be accurate and not precise. We can be precise and not accurate, but there are times where we can be both, and that is kind of the goal with data collection, is we want to be both accurate and precise. And so if we have all of our data points are really close together and they're close to the actual value, we know that we are both accurate and precise. So we see the both of them combined, and this is our goal. Okay, is to try to hit the bullseye with all of our marks. And so we strive for that. And if we don't make it, we just have to know why that might be the case, that we didn't get both accuracy and precision in our data values in a lab. Oops. So moving on, how do we actually analyze that through a lab? So we have error analysis, which tells us how good our data values are. And so the first one is percent error, and percent error evaluates how close data are to the actual number. So that would be accuracy. And in this case, we have an equation that is percent error is the actual divided by the experimental value. So this would be what you get in lab. This is actually the value that we know that substance should have. Okay, and we divide it by the actual, and then we also, to get a percent, have to multiply that by 100. And we will do this quite frequently in our labs. We can also use standard deviation, and standard deviation is using the numbers that are close together. So it evaluates how close our data are to each other. So this would be precision that we would be measuring by doing that. And it represents the average variation of data points above and below the mean, which is kind of like saying it's the average of the averages. And there's another equation that we use with this. I have a different video that explains how to do that, working it out with an equation, and oftentimes we do that in spreadsheets. So we'll take a look at those as we work through a variety of different labs this year. So the actual measurements that we're taking, we want to do a good job taking measurements and know how to use each piece of equipment well. But we need to know how many numbers we should be writing down, and that really is determined by the instrument that we have. Some of them give a digital readout, so it's really nice and easy, but our graduated cylinders are probably one of the toughest ones that we have in the lab. So all measurements have some uncertainty, and that doesn't mean that you look at it and you go, I don't know. Okay, it means that we have to have some values that we do know. So we know each one of these graduated marks. And so on any instrumentation, we know the mark values that are there, but then we have to estimate between two marks. And so that's what happens, is we estimate where substance is between two smallest marks. Okay. The significant figures, sometimes called significant digits as well, are all known marks plus one estimated value between two smallest marks. So let's take a look at how this plays out on our graduated cylinder. Remember, when we read a graduated cylinder, we want to read at the bottom of the meniscus, which is kind of the bottom of that contact lens looking thing. And so we're going to be right down here, okay? Well, that's actually between two marks. Even if it's on a mark, we need to know the values of each one of these things. So here's 15 and here's 20, which means here's 16, 17, 18, 19, okay? So, and then that mark halfway between there, that's going to be the 15.5 mark. Well, we know this is partway between the 15 and the 15.5 mark. And so because we know to the 0.5, that means we can estimate, okay, so this is what we know. We can estimate to the 0.00 mark. So this is going to be our estimated value. If it's right on the line, it would be 0. If it's not right on the line, then we have to estimate what that value would be. So it looks like it's about a half of 0.5, and I know that a half of 0.5 is 0.25, and so I would say that my measurement here is probably 15.25 milliliters. Okay? So it's really important that we pay close attention to what we're doing in lab with significant figures. You probably will get more experience actually looking at these numbers when you are looking at them on paper, however. It's important to do that in the lab, but we probably see more of this on paper. So let's talk about how we determine the number of significant figures if we're just looking at a value of data that are going to be on a piece of paper. So one thing that we need to know is all non-zero numbers are significant. Okay? And I'll give an example of each of these in just a moment. We know that sandwich zeros are significant, so the equals means they're significant here. Placeholders are not significant. And then zeros right of the decimal at the end of the number are also significant. So let's get a couple examples of each of these. Okay. So non-zero numbers, if I have a number like 186, okay, I'm going to have 3 significant figures. All 3 of these are significant because they're all non-zeros, and we know that all non-zeros are significant, so that would give us 3 of them. Let's take a look at sandwich zeros. So what if I had a number like 2005? Okay. Well, we know that this one is significant, and we know this one is significant. These zeros are sandwiched between the significant figures because these are non-zeros, okay? And so they are also going to be significant. And so in this case, we end up with 4 significant figures. The placeholders are the ones that usually people get confused with. So the placeholders and the zeros right of the decimal and end of the number. So placeholders would be something like, say we have the number 500. Okay. This one is significant. This one, these 2 here are just holding the place of the 5. They're very important. If we took them out and had 5, 5 is not equal to 500, so they're very important, but they're just holding the place value, and so in this case we only have 1 significant figure. On the other hand, say we had something like 0.005, okay? Again, these are all just holding the place of where that 5 is. We can't take them away, but they're all just holding the place value, and so this is also 1 significant figure. Now, we do have cases where we have zeros right of the decimal and at the end of the number where they are significant. So let's take a look at a couple of these examples. So here we have 500.0, okay? Now, it's the same number as we had up here, but now we have a decimal or a 0 that's right of the decimal and at the end of the number. That makes this one significant. We know that 5 is significant because it's a non-zero number. Now, what do we do with these 2? They're sandwiched between 2 significant figures. So we know that both of these are now going to be significant because these 2 follow into this rule. Okay? And so that means that we have 4 significant figures with this one. Let's try one more. My last one, we'll take that number that we had above, so 0.005, but I'm going to add a 0 after it. We know that these 3 are not significant because they're just placeholders, but this one is at the end of the number and right of the decimal, so that makes both of these significant, and now we have 2 significant figures. Okay? So hopefully that's helpful. We'll do lots more practice in class, and this is something you can come back and refer to or ask questions about later as well. So once we can determine them, that's kind of the first thing. And then what we need to be able to do is calculate values and report our answers to the proper significant digits. And so here is the rule for adding and subtracting. When you add or subtract, you report your answer to the fewest number of sig figs right of the decimal. I'm not going to go into why we do that necessarily, but if you have questions about that, feel free to ask. So I'm going to do an addition one first. So I'm going to start off with the number 4. I did this ahead of time, 5, 2, and I'm going to add that to 10.1. Okay, so when I add them, I get 14.62. Now, when I look at these values, I say, okay, which one of these numbers has the fewest number right of the decimal if they don't have the same? This one here has fewer right of the decimal, and in fact, we only have one right of the decimal, which means we have only one right of the decimal that we should have down here. Now, we have to use that 2 to figure out if we have to round up or stay the same. So since this 2 is actually less than 5, that means that this number here is going to stay the same. Okay, so we're not going to have to round. So that means our significant figures, our answer with significant figures should be 14.6, and that would be our answer. Okay. Let's try one with subtraction. So with subtraction, we're going to have the same rule as with addition. So we're going to have 18.59 minus 3.2. Okay. And so that gives us 15.39. Again, this number here has the fewest number of significant figures right of the decimal. So we only have one right of the decimal. So that means we're going to only have one right of the decimal. Now, the 9 is actually going to be greater than 5. And so that means that we have to round this up. Okay. So our answer with proper sig figs is going to be 15.4, and that would be the way that we would report our answer. And a lot of times I'll do this and then write the correct answer if that helps some of my students to be able to calculate those and then figure out sig figs. Okay, so always do the calculation first and then the sig figs. Okay, let's take a look at multiplying and dividing because the rule is just a little bit different. When you multiply and divide, you report your answers to the fewest total number of sig figs. So let's do a couple examples. Okay, first one we're going to do is we're going to multiply. Oops, keep that there. So I did something easy here, so we're going to do 2.5 times 3.00. Okay, and when we do that, we get 7.5. Now we have to know if 7.5 is going to be correct. Well, which one of these two numbers has the fewest total sig figs? Okay, this one here has the fewest total sig figs. And so that means that our answer should also have only 2 sig figs. So this is our fewest with 2. So our answer should also only have 2, which it does just as it is, so our answer is good. Now when we go to divide, let's try a little bit different one. Let's make it just a tiny bit harder. So we're going to do 25.0, okay, and I'm going to now divide by 8.0. Okay, again, we take a look at these. We're going to do our math first, okay, and we end up with getting 3.125. Now, after I've calculated, I go back and I go, okay, this one had the fewest number of sig figs, okay, the fewest. And so what I want to do is I want to go, okay, there's only 2 sig figs here, so that means this one can also only have 2 sig figs. So to write this with the proper number of sig figs, I'm going to say we have 3 point, okay, and we're going to use our 2 here to see if we need to round this number. And it looks like 2 is less than 5, so we don't need to round. So that's just going to be 3.1, and that would be our answer. Okay. So it's not always just going to be 1 after the decimal. It's going to depend upon what's going on. Sorry, my family is having a conversation. Anyways, I hope that was helpful. We will look at these when we get back to class, and until then, have fun using sig figs.